Hi, my name is Neely Dupuganti, and I'm going to be presenting the second lab we performed for Physics 2212, which covered lines of charge. The fundamental principle that this lab was based on was that ordinary objects like tape appear neutral. However, when neutral objects are rubbed together, they can acquire a temporary charge by gaining or losing electrons. The objective of this experiment was to determine the amount of excess charge on a piece of tape. Unlike Lab 1, in this lab we aimed to obtain a more precise approximation of the excess charge by treating the tape as a line of charge rather than a point charge. In the experiment, the charge on the tape was calculated to be a positive 1.127 times 10 to the negative 8 coulombs, which was greater than the calculated charge from Lab 1. In this presentation, I will cover how the charged tape was created, its interactions with other objects, how I calculated the excess charge on the tape, and I will conclude with answering the additional questions. To begin the experiment, a single piece of charged tape around 20 centimeters long was obtained and placed on a flat surface to serve as a base tape. Then, another piece of tape of 20 centimeters was placed on the base tape. After quickly ripping up this upper piece of tape, it was placed on a table end. The tape visibly acquired a temporary charge, as evident by its interactions with ordinary objects. When a hand was placed near the piece of tape was strongly attracted. When another charged piece of tape was placed closely near the tape piece is repulsed. When a neutral object, such as a book, was placed near the charged tape was strongly attracted. Finally, when a negatively charged pen was placed near the tape was attracted. This was an important observation because it indicated that the tape was positively charged and has a deficiency of electrons. After the sign of the charged tape was determined, the interaction between two pieces of charged tape was critically studied. The distance at which the tape pieces repulsed each other was measured. Because the momentum does not change, the net Y force is zero, so the electrical force and gravitational force must be equal and can be calculated by measuring the mass of the tape. To calculate the amount of excess charge, first the gravitational force on the upper piece of tape had to be calculated. As evident by my attached work, the magnitude of the gravitational force could be calculated by multiplying the mass of the tape by the gravitational acceleration, which was calculated to be 1.570 times 10 to the negative third newtons. Then, the distance between the floating pieces of tape was measured to be 0.025 meters. As evident by my free body diagram, the electrical force and the gravitational force are equal and opposite of each other. The electrical force is calculated by multiplying 1 over 4 pi epsilon naught by the charge squared over the separation distance squared. Through solving this equation, the approximate charge on the upper piece of tape was calculated to be 1.044 times 10 to the negative 8 coulombs. Finally, since the charge is positive, the number of deficient electrons was calculated by setting the total charge equal to the product of the number of electrons and the charge of one electron. The number of electrons was calculated to be 6.525 times 10 raised to the 10 electrons. Lastly, the ratio of deficient electrons to the amount of total atoms was calculated by assuming that the atoms are evenly distributed across the tape and have an equal chance of being taken up by another piece of tape. The ratio of the number of electrons to the total number of atoms was 1.307 times 10 raised to the negative 7. My computational model of this experiment visualizes the assumptions needed to calculate the charge on the tape. First, air resistance can be neglected. The lower and upper pieces of tape act as an evenly distributed line of charge. In my computational model, the line of red spheres acts as the upper tape, and the line of blue spheres models the lower tape. Further, each piece of tape is assumed to have the same charge. In the diagram, the white arrow represents the net electrical force on the red line of point charges. The yellow arrow represents the gravitational force. The green arrows represent the respective electric field produced by the blue tape for each respective red sphere location. The white electric force arrow and the yellow gravitational force arrow are seen to be equal and opposite. Using the code's functions, I calculated the approximate charge by testing different values for the charge until the electric force equaled the gravitational force. The charge on the tape was calculated to be 1.127 times 10 to the negative 8 coulombs, with the magnitude of the electric and gravitational force being 1.5696 times 10 raised to the negative third newtons. To conclude, neutral objects can acquire an excess or deficiency of electrons. Further, if the tapes were modeled as point charges as in Lab 1, the excess charge would be 1.044 times 10 to the negative 8 coulombs. However, when the tapes are treated as a line of charge, the excess charge was 1.127 times 10 raised to the negative 8 coulombs. The difference between these two approximations was 7.95%. Lastly, these estimates differ because of our differing models for the pieces of tape. Treating the tapes as a point charge assumes all charge is located at one central point, which is not true. This assumption simplifies calculations for the excess charge, but it does not produce a very accurate answer. Treating the tapes as a line of charge better models the real charge distribution and shape of the tape. This assumption treats the tape as a line of small point charges and produces a more accurate calculation for the excess charge, as it considers all vector components of each infinitesimal electric field, force, and charge.